Composition of functions is a new operation that we haven't talked about before. But basically, it's just the process of combining functions. So we've seen it done, we just haven't really learned the notation yet. So for example, in grade 11, you might have seen your teacher use a placeholder variable when you were trying to solve a quadratic trig equation. So for example, if you had a quadratic trig equation like sine squared plus 2 sine x plus 1 equals 0, they might have said let a equals sine x and rewritten the equation as a squared plus 2a plus 1 equals 0. And that just helped the quadratic stand out so that you could then solve the quadratic and then put the placeholder back in. So you're combining two functions there, the sine function and the quadratic function a squared plus 2a plus 1. So that was the composition of functions. We just didn't give it a name yet. Some new notation for multiplication for this unit, we're always using either fg or f times g written that way so that it's not confused with composition. Composition uses this little circle notation. So this is sometimes called fog notation because it looks like it spells out fog, or what it means is f of g of x, or that we're going to plug g in for x in f. So let's see how we might use a graph to do this. So let's call this f at x, and this will be g at x. And we want to find f of g at -2. So the other notation for this would be fog, so f of g at -2, they mean the same thing. But basically the inner function, g, or the function that's on the right-hand side, is the function that we start with. So g at -2, we're going to go over to our graph, which is the red one. And we are going to look where x equals -2. And we find that y equals -4. So g at -2 is -4. So now this question is, what is f at -4? So now we go over to our blue graph, our g at x, and we're going to go over to x equals -4, and we're going to trace up to our point, and then we read off our y equals 8. So our final answer, f at -4, is +8, sorry, not -8. So that's how you would tackle that kind of question. But what's interesting to note is that the first function you're working with, g, the output for g, so this -4, lines up with the input that you're putting into f at x. So that always has to happen. The y coordinate for the first function has to match up with the x coordinate for the second function, or it doesn't work. Okay, so let's see what this would look like with a set of points. So g of f of x, or g of f at x is the other way we can write that, is going to equal, start with f at x. When x equals 0, y equals 1. So now we want to know what g at 1 is. And the 1 matches up here, so the final answer is 2. So we started by plugging in x equals 0. We found f at 0 was 1. And then we did g at 1 was 2. So it's just the initial x value and the second function's y value that you actually record. And the ones just match up. The domain and range have to match up like that. Okay, so we're going to move on to the next point. So I'm starting again with f as the inner function. So I'm starting with x equals 1. When x equals 1, f at 1 is 2. And g at 2 is -1. Again, you have that range from the first function matching up with the domain of the second function. So, and I just record the original x that went in, 1, and the final output was -1. Okay, we're going to move on to the next point. 3 gives us 7, but now we're stuck because g does not have an x coordinate of 7, so this one doesn't work. So we're actually all done. That's all we can do for f, or g of f. Okay, so let's do the other way around. So we're going to do fog, or f of g of x. So now g is the inner function. So I'm just going to erase this. So now we are starting with g. When g is, or when x equals 1, g at 1 is 2, and there's no 2 up here, so that point doesn't work. When x equals 2, g at 2 is -1, and again that doesn't work because there's no -1 for the input in f. If we have x equals 5, 5 gives us 0, so g at 5 is 0, and f at 0 is 1. So there we do have the matching up of the range in the domain. So we have just 1 point in our answer. It's just going to be the original x. We started with 5 this time, so we're starting with g. The zeros matched up, and we got a 1 out at the end. So I'm going to show you this as well with kind of a set of function machines, because that might help as well. So we will say that f at x is going to be blue, and g at x we will say is red. So if we are doing f of g of x, what that would look like in terms of our function machine is this. I would take my initial input. So let's take the point that worked. So we have 5 worked. So we're going to take our initial input of 5. And we're going to throw that through the first function. So 5 is going through the first function. So here's my machine. And what is that machine doing to it? Well, it's doing something to it and it's spitting out a y coordinate. So g is acting on it, and out pops an output, g of x. So x goes in, something happens to it in that machine, g acts on it, and then it spits out g of x. That's how our function machine works. But our coordinate is 5. So 5 goes in, g does something to it, and it spits out a 0. Okay. So then the next thing that's going to happen is that that value is going to get plugged into f, the second function, or the outer function. So that g of x now goes into our next function, and that was our blue function f at x. So it looks like this. So it acts on g of x, does something to it with f, and then it spits out f of g of x, which is our final answer. Okay, so we are going back up to find 0, because 0 was our output from g. It also becomes our input that goes into f. So now we go to f, and we find that input of 0, and then our final output is 1. So 0 goes in, f does something to it, and then it spits out a 1. So this 0 is really important in that it has to line up. So 5 is the original input, this is the x, and this is the final y that comes out, or f of g of x. That's the point you're actually writing down. But there was this output of 0 that became our input that was really important and had to match up. So hopefully that kind of makes sense. Now let's see what happens if we plug in something that doesn't work. So if we plug in 1 into our first function, so if 1 goes in, we know it spits out, it goes through g, and it spits out, I believe it was a 2. And it tries to put it into the next function f, But the problem is that our function f actually doesn't accept 2's because we don't have any inputs of 2. There's no 2. So it doesn't like 2. F of x does not want a 2 as the input. So it says nope, it blocks it. It's not the right ingredient. It says no. So it doesn't accept it. So that's why we have no answer at the end either. So an x value of 1 does not give us a valid point. Okay, so let's look at what happens when we use an equation. So if you have g of x being x squared minus 1 and h of x being x plus 1, and we want to find g of h of x, or written in this notation, g of h of x, or plugging h into g, we want to know what g is at h of x, which was x plus 1. And so what we want to do there make this a bit smaller. So what we want to do here is we then want to take x plus 1 and put it into g wherever an x is. So we're placing x here with x plus 1. So where there was x, we're going to put x plus 1 squared minus 1. So we're going to end up with x squared plus 2x plus 1, because we're expanding x plus 1 times x plus 1, and then minus 1. So we end up with x squared plus 2x is our final answer. Okay, so now we're going to do the other way around. So we're going to do h of g of x. Okay, either notation's fine. So now h is my outer function and g is my inner function. So I'm plugging x minus 1 into h. So where I see the x here, I'm replacing it with x squared minus 1 plus 1, and that gives me just x squared. Because the minus 1 and plus 1 cancel out. Okay, we also have to be able to work with inverse functions because there's some special rules for inverses with composition. So just a quick review, if I have something like f at x equals x squared plus 1, and I want to take the inverse, step 1, I replace f at x with y, so y equals x squared plus 1. I switch the places of x and y, so x equals y squared plus 1. I isolate y squared, so I start by subtracting 1 from both sides. And then to get y by itself, I take the square root of both sides. So I end up with y equals plus minus square root of x minus 1. And then I put it back in function notation. And this is my inverse notation. Okay. So that was a quadratic example. The square root function, the top and bottom branch is the inverse of that. If I wanted, I should say it's not a function, no relation. The simpler example we're going to look at is just for a line. So if we have f at x equals x plus 1, we're going to say y equals x plus 1. Solve for y, interchange x and y. So x equals y plus 1. Solve for y, so y equals x minus 1, which hopefully isn't too surprising because the opposite or inverse operation of adding 1 is subtracting 1, and put it back into function notation. So what happens when we do f of f inverse of x? So we want to plug f inverse into f. We want to plug x minus 1 into f where the x was. So we end up with x minus 1 plus 1, which is just x. So that's an interesting result. Whenever we do this with an equation, we should just get back the input. So if we put f of f inverse of 2, we should get back 2. Whatever we put in, we get out because it just undoes the operation with the inverse and the original. Let's see if it's true the other way around. So f inverse of f. So now we want f inverse of x plus 1. And we want to do x plus 1 minus 1, which is also just x. So that's an interesting result, that if you plug an inverse into itself or vice versa, you should get back x, the original that you started with, and that can work with a number as well. It's a little different for a set of points because both of those functions that I just looked at were lines. They were defined for all values. It's a little bit more complicated with a set of points. So to find a set of points, the inverse for that, all we do is we interchange x and y. So 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. 3, 7 becomes 7, 3. So if I now want to do f of f inverse, it's going to look a little bit different this time. It's going to just be a set of points as my answer because we just have 3 points that we're working with. So f inverse is the one I'm starting with. So I have an x value of 1 gives me an output of 0. F inverse at 1 is 0. And then that becomes my input. F at 0 is 1. So I get 1, 1. 2 gives me 1. 1 gives me 2. So 2, 2. And the order is important here. 7, 3 gives me 3, 7. So 7, 7. So whatever I start with, whatever x values are in my first function or my inner function, that's what I end up with. This is not the same as f inverse of f like it is when we just work with an equation. And I'll show you why. It's because of the order. So this time I'm going to have f being my inner function. So this is 2. So I'm starting with f this time. And f for x equals 0, f at 0 equals 1, and 1 gives me 0. So 0, 0 is my first point. Again, it's the input that I started with, and then that repeated, the same input and output. So I start with 1, I get 2, 2 gives me 1, so 1, 1. And then 3 gives me 7, 7 gives me 3, so 3, 3. So it's a different set of points, but you still see that the input and the output are the same.